by taking any kind of questions that we might have from homework or other things. Mackenzie? Okay, first one. Okay. You can do that all in one interval because it's still increasing at that point -5. Like if you pick a point to the right or to the left of -5, you're still getting a positive slope in there. Correct. Oh, what's your name? Taylor. Thank you. For a domain? Okay. So for a domain or range, we would use a or equal to inequality if you actually have a point in your function or relation that has that specific x or y coordinate. So if you're talking about the domain for number 1, use a less than or equal to with the -6. We have a point that has the x coordinate of -6, right? So it should be an or equal to inequality. So if it was like an open circle there at the end, instead of a filled in one, it would be a strict less than. Does that feel okay there? Aside from the infinities, it always gets strict less thans, right? I should probably make mention of that. I am in terrible too.
It's okay.
Alyssa, what's the last name too?
Burrells.
Okay, that helps me, believe it or not.
For number 4 on the first one.
So homework 2 is what we mean by the first one?
Yeah.
Okay.
For like positive, are we supposed to put every single one of those dots on there? I was confused as to what we write.
Okay. Yep. I didn't realize I wasn't projecting my screen. Let me do that real quick. Okay. So this is what we're looking at, right? So if you look at that, there I actually tried to draw this so that you see there's a line in between the dots, right? So each of those represents a separate connected piece. You agree with that? So if I'm looking for the place where it's positive, I have all of these sections where it's positive, right? So if I'm going to write, one way I could do this by to write the positive parts is I could write a separate interval for each of these. Not incorrect to do that. However, what do you notice about each one of these, the x coordinates for each one of these pieces? They're not the same, not all of them anyways, but they are overlapping, right? Specifically, the last point and the first point overlap. We can see that. So really, because they all overlap, I could really just write it with one interval, where I could just go from the start to the end. Does that make sense,
yeah.
Alyssa? I'm going to keep using your name so I try to remember it. And that's a good question, right? Some of these got kind of tricky at the end. That's why I gave you the tricky ones now, so we can see them in the homework and talk about them. And you can think about like, oh boy, what do I do with this? That's okay. Bar. No. Amy, Donith. Okay. Okay. Well, there's only one part of the graph that's on the x-axis. It's right here. Well, the other ones matter if we're talking about constant, but not for 0. Remember, 0 is the location, whether it's, positive, negative, and 0 are about location, whether you're above, below, or on the x-axis. Increasing, decreasing, constant have to do with like the uphill or downhill or flatness. So it's easy to kind of get those guys turned around. But when it comes to 0, there's just one 0 section for this graph. You're welcome. And just tell me. I can't do it. My bar. Okay. So going back to number 1. So here I would say there is no constant because there is no flat section. The way that we are defining increasing, decreasing, and constant, singleton points can't fall in there because we're talking about slopes. In a calculus class, you would define those points as having slope 0, but not here. So you could just write none for the constant for this graph. Yes, sir. Tommy. Marvin, thank you.
So I think Mackenzie has like the same thing, but for the increasing, you don't have to go from -6 to -5. You can just go straight from -6 to -3.
Correct, because on that whole section, any 2 points you pick are going to have a positive slope between them, right? Yep, and that was what Mackenzie had asked. That's okay. You can ask again. Taylor. Okay, so here I notice there are 4 disconnected pieces of the graph, right? And I notice that none of these pieces are overlapping, at least in the x direction, right? So I'm going to have 4 distinct pieces for my domain, and I'm just going to do I'm going to do it separately for each piece and just put a union between them. Do we need to do that, or is that enough direction? Let's start anyways. So I see 4 distinct pieces. I see this piece, this piece, this piece, and that piece. You agree with that? And none of them overlap x coordinates, right? Any of those pieces. Everybody agree with that? So the domain I can just do separately. So I start here, and I'm going to go start to finish. We start at -6 and we end at -2. And those are absolutely x coordinates that are used on that section of the graph, so they get brackets, or the or equal to inequality, if you're writing it as an inequality. Okay with that, Taylor? And then I'll do a union, and I'll do the same idea here. And then I'll do another union. I'll do the same idea here, except I can't use an interval for that one because it's a single point, right? So there I would just use like my set notation with the x coordinate. And I'll do another union and the last piece. Okay with that? The range is a little trickier because we do have overlapping y coordinates, right? So if I look at this, the only 2 pieces that really matter for my range is this piece and this piece, because these 2 pieces overlap with the thing that I circled in the green. All their y coordinates overlap. So I can just write the ranges for those 2 pieces separately, and that's it. Does that help without telling you exactly what the answer is? Okay. Mackenzie, you were going to ask a question here?
You write your domain as like just put it
You should, yeah, you need to put the unions in between them. It's not like super wrong to not do it, but it's like kind of wrong to not do it. You know, like if that's a, 3 or 4 point question, I'd give you like 3.5 out of 4 or something. So like a small deduction, but not like a massive deduction. Does that help answer what you're getting at? Okay. Amy, look at me learning names here. Yes. Yeah, so it's because it's going to the right. This arrow that's going up and to the right, because it's going to the right, is like positive infinity, because that's on the x's. You go to the right, they're getting bigger. And because it's pointing up, the y-coordinate's like positive infinity. So depending on whether you're doing the domain or the range, that's kind of the way I would treat that last point. Or the arrow at the end of the graph, I should say. It's not a point per se. But that, I think, helps conceptually, right, if you're able to do that. Okay. And that's all you're asking, right? Okay, perfect. These are good questions, guys. These are absolutely ones that are like, I've been thinking about this and I'm not really sure what to do, which is kind of the point of some of these problems, is I'm giving you weird stuff that's happening, because if you understand the weird stuff, the straightforward thing should be straightforward, right? And you're asking a lot about the notation, like, do I have to do this in this case, or can I just do this? And those are great questions. Exactly the kind of thing that you should be asking on these, during this kind of time. So that's very good. So keep it up. Anyone else? I think this sheet is more difficult than homework 3 was, right? Homework 3 should have been relatively straightforward. Okay. Any last takers? Yes, Alyssa.
Yeah.
Or Alice.
Yeah. The homework 2, question 4, how would you do the constant? In other words, it wouldn't be any increasing or decreasing.
Right.
So how would you write that with all the numbers?
So this one, the question becomes, can you write this as one interval, or do you have to write it as like a bunch of different intervals? What do you think? Because this is an important question, right? We're able to do the domain or the, by just writing one interval, or the positive or negative just writing one interval. Can I do the same with a constant? No is correct. Why not? Right. Like if I pick a point here and a point here, the slope in between them isn't 0, right? So you have to write them all as separate. Good. So again, like the more technical definition sometimes on these ambiguous cases is really what we have to go back to, which is good, right? Force us to think a little bit harder about what's going on and what does this really mean, because it's flat everywhere, but it's not the same flat everywhere, which is weird, but okay. All right, so let me rehash a little bit what we did last time, just so I can start talking about the stuff that we need to talk about. So we did this. Okay. So we haven't done extrema yet. And we haven't done the stuff with the calculator, and then we need to talk about transformations. Got it. Okay. So that's I made a list for myself already of what I wanted to do here today. I was ahead of the game, and then I forgot that I got ahead of the game. What a bozo am I? Does anybody remember where attribute we're on? Are we on 4, I think? Right, we did positive, negative, 0, increasing, decreasing, constant, and then end behavior. So I think we're on attribute 4. Okay, you guys agree? All right. So this next attribute is called extrema. And the extrema are just the relative highest or lowest points on a graph. So there's 2 types of extrema. One type are maxima. Maxima is just the plural for the word maximum. And the other type is minima, which is just plural for the word minimum. Maxima are the highest. And minima are the lowest points, respectively. And there's 2 types of maxima and 2 types of minima. So you have global maxima or minima. And the global maxima or minima are just the overall highest or lowest point. And then you also have local, which is the highest or lowest point kind of in its general neighborhood. Okay, so let's draw some examples here to kind of get a feel for this vocabulary. Sound good? Okay. So let's say we have this graph. How many maxima do we see on this graph? 2. Good. I see one right here, and then one right here. Everybody okay with that? The one on the left, is that a local or global maxima? That's global, right? Because it's the overall highest point. And then the one on the right is a local. Everybody good there? How many minima do we see? 1. There's 1, it's right here. Why don't these guys count as minimum? Because they're going on forever, right? Any point you pick, there's another point lower than that. So like they can't count as a minima. So this minima we've established, is this local or global? Just local, right? So what we notice is there's no global minima for this function. So we have arrows pointing down, so there's always going to be a point lower than whatever we found, right? Could you have a function that has neither global maxima or global minima? Yeah. What about just something like this? And where I have an arrow pointing down and an arrow pointing up. In fact, does this have any extrema at all? No, right? There's not even any locals in this. Is everybody okay there? So you can see we can have no extrema. Can I have both a global maximum and a global minimum in the same graph? Sure. What would that look like? Well, just doesn't have any arrows on it, right? There, we have a highest point and a lowest point, right? Can I have a graph that has more than one global maximum? Sure. What would it look like? Yeah, two at the same height, right? So you can have more than one, like global maximum. Could I have infinitely many? What would that look like? What about a section like this? Right? All of this is a global maximum, right? Those are all tied for first. All the points on that flat section of the graph. And all these things that we've been talking about, maxima, obviously apply to minima too, right? If you just flipped any of these graphs that we've talked about, we could say the same thing about the minima. Everybody's okay there? What do you guys think? You think you got this? This is about all I'm going to need for you to do as far as like without a calculator. Is just being able to look at a picture and identify how many there are, which is not too bad, right? Fairly easy to find them. What if we actually wanted to find the coordinates for one of these extrema? That's actually a very difficult question. In fact, until you take a calculus course, that's not a question that we're going to be able to solve algebraically. However, our calculator can handle that and give us a very precise approximation. So let's take a look at how to do that on our graphing calculator. So if you have your graphing calculator, I invite you to take it out and follow along with me. If you don't have it with you, that's okay, because we're recording what we're doing here. So you can always go back and look at the recording and follow along at home. Or if you followed along here and you forgot what to do, you can always go back to the recording and follow along at home. Or if you're just like, I have my calculator here, but I'm just going to sit and pay attention because that works better for me than trying to follow along, that's fine too. Okay? So I'm going to fire up my graphing calculator emulator here. And it should be, there it is, okay. Oops. All right. So let's begin by turning our calculator on. The on button can be located in the lower left-hand corner. I know you're snickering at me for telling you how to turn your calculator on, but some of us has probably never turned their calculator on at this point because they might have just got it this year. So we're going to be like that specific about things. Before we go on and describe what else we're going to do, let's kind of describe what it is that we're asking, what information we need to give the calculator and what we're going to ask the calculator to do, kind of in broad strokes, because I think that helps understand what it is that we're doing. So what we're going to do is we're going to give the calculator the equation for a function. The calculator is going to interpret that into a graph. We're going to visually identify where the maxima and minima are on the graph. And then we're going to give the calculator like 2 points to look between to find that highest or lowest point. So the calculator needs an equation from us. It'll then turn that into a graph. And then from us, it needs to know between what 2 points do I need to look for either a maximum or a minimum. Okay with that idea? Okay. So the first thing we're going to do is we're going to tell the calculator what equation we want to graph. So for the sake of argument, as an example, I think that's what I have in there. So this is what we're going to graph. I'm just going to write it here so when it comes time to type in your calculator, you can see what it is we're going to type in, okay? So if I want to graph anything on my calculator, the place that I need to go is to the y equals button, which is located in the upper left-hand corner of our calculator. Oh, I meant x plus 2, I guess. Sorry, I couldn't remember for sure. So when you press the y equals button, it's going to take you into this menu. Notice on the left we have all these y equals there already for us. Take a moment and scroll through all the way to the bottom and make sure that you don't have anything typed into any of these spots. If you find something in there, like I found this one that has an 8 there or something, you can get rid of the whole line by just pressing the clear button. The clear button is directly below the down arrow. So you go all the way down, make sure there's nothing there. You have 10 spots to check, particularly if you've had this calculator for a while and it's been sitting in your backpack all summer. Buttons accidentally get pushed and you get gobbledygook in here and it causes problems later on. It's difficult maybe to catch. So before I graph anything, I usually take a quick pass through and just make sure that I don't have anything else typed in there. Everybody's okay with that? Okay. So now in the Y1 spot, I'm going to type in this function exactly as it's written. So my calculator's already put the y equals in there for me. I'm just going to type in the rest of it. So notice the parentheses are above the numbers 8 and 9 on the keyboard. The variable x is next to the green alpha button, kind of in the upper left-hand corner there. And then the numbers are on the main keypad and the addition, subtraction, division is off on the far right side. Make sure when you type the subtraction symbol, you use the subtraction symbol and not the negative sign symbol. The calculator treats those differently and you'll get an error if you're trying to use the negative sign as the subtraction symbol or the subtraction symbol as the negative sign. So they are distinct symbols on the calculator. Okay, I'll give you guys a minute to kind of make sure you've got that typed in. Notice that on mine you can't see the very end of it because it goes off the screen, but it's still there. Like I don't think you can see the 3 at the end of the x minus 3. But it's still there. You can trust me. Now that we have this typed into our calculator, we need the calculator to produce a graph for us. In order for the calculator to produce a graph, it needs to know, like, okay, there's infinitely many points on this thing, like, between what values am I going to graph this on? Like, what does the piece of graph paper I'm going to plot this on look like? So I know what points I really need to generate and what points I don't. So, in general, unless you know something very specific about what you're planning on plotting, I usually start with just from negative 10 on the x to positive 10 on the x and negative 10 on the y to positive 10 on the y. That's the kind of the piece of graph paper that I'm going to ask the calculator to graph the function on. And I choose that because that option is already programmed into our calculator. I don't have to set that manually. So to choose that option, what I'm going to do is press the zoom button that's in the middle of that upper row of keys. And from the options there, I'm going to pick the Z standard. So that's option 6. So you could scroll down and press enter, or you could just type in the number 6. And it should give you something that looks like this. Anybody have an issue to this point? What does the error say? It's already there. If you just hit graph, it'll give you that same error again. on the upper right, that top row on the far right, is the graph button. So that just switches to the graph view.
Okay, the second argument is like graph plot at
It doesn't say like syntax or something?
Oh, yeah, so, yeah.
Okay, so that means you're using a symbol inappropriately somewhere. So if you go back to your y equals, it's going to be in that spot. So it's either the equation you typed in has an error in it, but if you saw the graph for a second before it flashed out to an error, I don't think that's the issue. I think you have something in one of the y equals spots that you can't see. So if you scroll down.
My 10 is 10 screwed up. Like why? I don't know if that's supposed to be like that or what happened, but
Yeah, so just hit clear.
that makes sense.
And now if you hit graph, everything should work. You're welcome. I can't see your face. Loretta. Okay. So that happens fairly regularly for students. To fix that, if you get an error, invalid dimension, if you go back to the y equals, Loretta, up at the top where it says plot 1, 2, and 3, notice none of mine are highlighted. I bet one of yours is, or all of them are. So you can just move up there using your up and down arrows, and just press enter to unhighlight them, and then hit graph again, and everything should be fine. You're welcome. Okay, so now everybody that's following along has a graph that looks relatively similar to this. In fact, it should look almost identical, right? Okay, so what we need to do now is we need to visually inspect this and find how many maxima or minima are we looking for. If you look at this, how many maxima do we see? I see one local, right? And now how about the minima? One local also, right? Our maximum is here, and our minimum is there. Everybody agree with that? Okay. So what I'm going to do now is I'm going to press second and the trace button. The trace button is right there on that top row of keys. This opens up the calculate menu. You might have noticed above the trace button in blue says the word calculate. Those words in blue above the buttons are the second, and then that button, what it does. So this calculate menu is all these options are things that you can use on a graph. If I'm looking for the maximum, which one of these options looks like the one that I want? Option 4, labeled maximum, right? So you can either scroll down with the up and down arrows to 4 and press enter, or you could just type the number 4. Either will work. And now notice it returns us to the main screen, but in the lower left corner of our screen, we have a question. It says left bound with a question mark. You guys all see that? You should also notice that on your screen somewhere, you have a cursor that's flashing. My cursor is flashing here at the origin. Yours may be at a different location. That's fine if it is. What we're going to do, what the left bound is asking for, is the calculator is asking for a point that's on the left side of that maximum. So I'm just going to use my left or right arrows to move my cursor so it's somewhere, anywhere left of that maximum. So this spot looks good to me. Notice I've moved my cursor over to here. There's nothing magic about that spot. As long as it's on the left side of the maximum, it's fine. Once I've done that, I'll press enter. Notice now the question has changed. It says now right bound with a question mark. So I'm going to just move my cursor now to the right side, somewhere over here, of that maximum, using my left or right arrows. So that looks good, and I'll just press enter there. Yes, Amy. So you accidentally pressed enter twice. So after I pressed enter for my right bound, you'll see that mine says guess now. So you just accidentally pressed it, like I think the enter button one too many times somewhere. Okay with that? Okay. So that's, I think, all that happened. You might need to start over, at least from the maximum part, like back to that second trace menu. Yep. And now the guess. So the guess is asking you to guess where the maximum is. Let me tell you a secret. If you put that guess close to where the maximum is, the calculator will find it faster. But in terms of computing faster, what we're talking about is like a few microseconds. It'll take less time than it would if you picked a guess right where the cursor is currently at. So I usually just pick wherever I'm currently at for my guess. I don't bother to move it close because it doesn't really make any difference in terms of my wait time. You see that almost instantly the calculator found a response because what I'm asking it to do is not really that difficult, at least for a computer. There's a lot of calculation it just did to find that, but it's a computer that's good at doing repeated calculation really quickly. So what I have here then is the point negative 1.19631, comma 4.0606726. Now that's an approximation, but it's an approximation out to like 9 decimal places, which is a pretty darn good approximation. So if I was looking for an answer, I'd probably ask you to round this somewhere. So we have a local max. Let's say we round it to 3 decimal places. So the x-coordinate rounds to negative 1.120. And the y-coordinate would go to 4.061. That's just rounding to 3 decimal places, which is probably what I would ask you to do in most settings. It's enough to make sure that you're able to do this process because there's no way you shouldn't be able to get an answer accurate to 3 decimal places without doing this, without forcing you to write down like all those decimal places, which is just kind of tedious. Let's find the minimum now. So we'll just press second and then the trace button. But this time I'll pick the minimum command. And I'll do that same left bound, right bound, and guess, but this time I'm doing it relative to the minimum. So that point is left of it. That looks good to me. Again, doesn't really matter. And that part looks to the right of it. And then the guess doesn't matter. So there's my minimum. So I'll call that first the x-coordinate 1.786 and the y-coordinate negative 8.209. That's basically all there is to it as far as the calculator goes. Not difficult, what you're asking the calculator to do, right? Requires very little from you. Now you have to know where the commands are and how to use the commands. But from a mathematics standpoint, like the hardest part about it is like looking at the graph and identifying where the extrema are. Like that's the only thing that would classify as like mathematics for you. The rest of it is just knowing how to use the calculator. Mackenzie. So for the left bound and right bound, so it doesn't really matter. The left bound is anywhere left of what you're looking for, and the right bound is anywhere to the right of what you're looking for. So that doesn't matter. Like anywhere. I mean within reason, but anywhere almost is fine. Does that do it? Alyssa.
What's the purpose of the left and right bound?
So the calculator is doing an approximation, and basically it picks a point in between the two, and then it stores that, and then it picks a point between that and the ends, and if that point is higher, if it's looking for a maximum, it now stores that one, and it just basically like doing an elimination down till it finds the highest point in between them. So it needs some place to like, I'm only looking between these two things. If not, there's never an end to it. Like if it's going to check all these points, and even here there's infinitely many points, but not really. Like the calculators has like a, like a mesh when it's generating these points, so it's not finding all the points, it's just finding them so that like the x coordinates are like some tiny decimal difference apart. So it actually has like, 2 million points or something that it's looking at.
And then you just like, I'm confused because I missed the part of the graph, but so it says like left down, you click something on the left and something on the right.
Mm-hmm.
And after enter, it says guess.
Yep, just press enter where you're at.
Okay.
It doesn't matter. I mean, it matters, but it doesn't.
Oh, okay. Now I'm good.
And then it spits out the value.
Oh.
Good? Okay. Yes, sir. Zach?
Yeah.
Okay.
Does the calculator tell you whether to go left bound or right bound?
Yes.
Okay.
So it starts on the lower left-hand corner of the screen. It's going to say left bounder with a question mark or right bound with a question mark.
Then you move your cursor there and press get.
Press enter. And then it'll change to the other one. You move over, press enter, and then it says guess, and you can press enter just where you're at. And then it spits out the answer. So it's pretty easy to use once you do it once or twice, and it's like, okay, not bad. Remembering where all the menus are and all that stuff, like that can be hard your first couple of times doing it because it's a brand new tool you've never used before. But if you can use a cell phone, like your smartphone is far more difficult, far more complex than your graphing calculator is. It's just the operating system is very different from it, so you're just not familiar with it. It's more like an old Windows 95 machine than it is your smartphone, which is why it seems so foreign to you guys, because you're all probably born after 1995. In fact, surely you were. You'd be a 25-year-old sophomore or junior, which would be kind of weird. All right. Do we feel okay with the calculator part? If you don't, we'll take questions or whatever next week when we come back, and it won't be a big deal, right? All right. The last topic that I want to talk about is transformations of graphs. So I'm going to start by asking you to recall a little bit from geometry, because I'm going to use this as kind of a foundation for what we're about to do. Because you did graphical transformations in geometry. You talked about 4 different types of transformations. Does anybody remember one of those? Amy. Reflection is one of those types, absolutely. Good job. So in this class, we're only going to worry about 2 types of reflections. So we have those across the x-axis and those that are across the y-axis. But you can really reflect across any straight line. But in this class, those are going to be the 2 that we really focus on. Yes. What's your name?
Jack.
Jack. Dilation is one of them. Yep. So the dilation is the one where it's like you're expanding the figure or contracting the figure. That's good. There's 2 more. No. Sergio?
Rotation.
Rotation is another. Yep. So this is actually something quite difficult to do if you're talking about the graph of a function, and it's beyond the scope of this class, so we're not going to worry about those. But they are a type of transformation you did in geometry, and that's exactly what I was asking you to do. This is one of the 4. I'm just letting everybody know we're not going to do that in this course. And really, I don't think you'd ever do it as a high school student. I think you'd probably need some linear algebra tools to be able to do this effectively, so it'll be a while. Well, you need trigonometry, and then you probably need linear algebra in order to do you probably use a matrix to do the transformation, and you don't know what that is yet either. We'll talk about matrices a little bit in this class, but there's a whole field of mathematics built around doing algebra with these matrix objects called linear algebra. And you can spend a career studying linear algebra. But anyways, continue on. There's one more. I think it's the easiest of the 4, but it's probably the hardest one to remember because it sounds so much like transformation. It's the translation, yeah. So just to review, reflection is like you're flipping it over the x or the y axis. The dilation is like you're blowing it up or shrinking it down. The rotation is you're spinning it around some point. And translation is like you're just picking it up and moving it. So you go left or right some amount and up and down some amount. When you guys did this in geometry, you probably used like a little transformation map to describe this. So like to reflect across the x-axis, you take the old or your original xy's, and then you negate the y-coordinate, and it'll flip it. Similarly, if you want to reflect across the y-axis, we negated the x-coordinate. For a dilation, this was a multiplicative thing. Now, I think in geometry you always did a symmetric dilation where you multiplied the x and y coordinate by the same number. That need not always be the case. Like you could, stretch in one direction and kind of shrink in the other direction. It's weird to kind of think about that in a geometry context, but it's perfectly reasonable if you're talking about a curve to want to like stretch vertically and compress horizontally. And sometimes it's really the same thing, but sometimes it's different. So I'm going to use 2 different letters there, A and B. They could be the same number, though. Keep in mind, A and B could be equal. There's nothing wrong with that. And then the translation, this was just where we added a value to the x or y coordinate, respectively. And again, I'll use 2 different letters there. They could be the same letter, but I think even in geometry, you did we shifted it left 4 and then up 7 or something. Like that was not unreasonable for you to have done. Is everybody okay here? Okay, so these transformation maps were pretty useful. If we put this all together, if I'm doing all of the other than a rotation, but if I'm doing the 3 transformations that we talked about there all at the same time, that's what the transformation map would look like. And that's something that'll be pretty useful, and we'll return to this at the end when we do some examples. Yes?
Is that AY plus K then?
Yes. Yep. So it's bx plus h, comma, ay plus k. Now, in geometry, it was perfectly reasonable to just worry about these transformation maps, right? And typically, I think in geometry, you would do like the transformations one at a time rather than all at once, like this is doing. But that's fine. Now, in an algebra classroom, when we're describing our sets of ordered pairs, instead of just having to worry about like the 3 vertices of the triangle when we're doing our transformation, we have like infinitely many points on a curve, right? So the notation we're going to use is going to be a little bit more convenient for that sort of situation. So we have some original function that I'll call y equals f of x. In algebra, we often refer to this original function as like your parent function. In geometry, you called this like the pre-image, I think. Was that what you called it? It's been a minute since I taught the geometry course. So you had something and then you transformed it. You had the pre-image, which was your starting point, and your image, which was the result. I think is the verbiage you guys use. Yeah, so the parent function is like your pre-image. Okay, it's whatever you're starting with. So any transformation of y equals f of x can be written as g of x equals a times f of 1 over b x minus h plus k. Now, in this class, because the types of functions that we're going to study, the a and b coefficients are really going to do the same thing almost every single time. So more often than not, we're just going to write it in this fashion. And when we get to these, start talking about these specific function groups, I'll explain to you why we can really simplify it down and get rid of that b coefficient. But it'll be a minute. You know, chapter 2, this next chapter will be the first time I kind of make this argument as to why we can ignore that. But more often than not, we can. But we'll get to that as we go. Okay. So these a, b, h, and k are each going to be, or is going to, each one of these coefficients is going to describe some kind of transformation. And no matter what type of function we're talking about, we're going to describe the transformation in the same fashion, where the a, b, h, and k do the exact same things. So this list of criteria that we're going to go through right now is going to be the same the entire year, which is nice, right? We'd like to be able to give one set of criteria that always is the same every single time, so it's not different. You know, if you're talking about a square root function or a logarithmic function. Again, you don't know what either of those two things are probably, and that's okay. We'll talk about both of them this year. But we're trying to lay a foundation that's going to work the whole time. Okay? All right. So, let's start with lessons. So if that a coefficient is negative, we have a reflection across the x-axis. If that a coefficient is positive, we have no reflection across the x-axis. Keep in mind the a coefficient cannot equal 0. Why can't the a coefficient equal 0? If that's 0, that just simplifies down to k, right? Because 0 times anything is 0, and then you're just left with plus k. If you have a function that's equal a constant, all you have is a straight line, which is not going to represent a transformation of anything, right? So that's why we just ignore the condition when a can be 0, because it doesn't make any sense. The magnitude of a also matters. So if a also creates a dilation effect in the y direction, so if that a or the magnitude of a is or greater than 1, we have a vertical stretch by a factor of a. And if it's less than 1, we have like a vertical shrink by a factor of a. And if it's exactly equal to 1, we have no vertical dilation. I abbreviated vertical with just V period there. I hope that's okay. So the A coefficient does two things, right? It dictates whether there's a reflection or not, or a dilation, a vertical dilation, I should say. So if we're stretching or shrinking vertically, like we're pulling up, like you're a piece of Laffy Taffy, or squishing down like you're in a cartoon and like an anvil just fell on your head. Trying to find something that's like, you know, some common shared experience. So probably most of us watched a cartoon where the Roadrunner dropped an anvil on the coyote or something and it like squished him down. Okay. Next up, let's talk about the B. So if the B is negative, we have a reflection across the y-axis. And if the B is positive, we have no reflection across the y-axis. If the magnitude of B is bigger than 1, we have a horizontal stretch by a factor of B. And if the magnitude of B is less than 1, we have a horizontal shrink by a factor of B. And if it's B is equal to 1, we have no horizontal . Okay. The last two coefficients we have to talk about are the h and the k. So if h is greater than 0, we're going to just translate to the right h units. If it's less than 0, we're going to translate to the left h units. And then lastly, we have k. If k is greater than 0, we're going to translate up k units. And if it's negative, we're going to go, surprise, surprise, down k units. Yes, sir. Here's what I'm going to say. I'm going to say yes because we use it in chapter 2 and 3 and 4 and 5 and 6 and 7. Basically, the entire year will refer back to this description of transformation. So I say yes because just because it's used really almost every chapter. Yeah. Yeah, you'll end up doing it on your own because one of the questions I'll ask is like, okay, describe this transformation in words, and you'll go, okay, and you'll need this criteria in order to kind of do that. And you'll have done it enough times that it's like, well, I guess I better just memorize this, and it'll make sense. Actually, let's make it make a little bit of sense right now. I see people still writing, so I'm going to kind of jog here in place a minute while people kind of catch up with that. But I'll kind of describe to you, going back and looking at that transformation map, an easier way to remember some things. Because again, this is a mighty list, right? There's a lot of stuff going on. But if we kind of think about it in a little bit of common sensey, it helps. And I can help do that, right? If it makes sense, it's always easier to remember than if it's just like an arbitrary list. At least to me. I was a kid that like, my worst classes were like, you just have to memorize this and there's no rhyme or reason why this list exists. Like biology was a nightmare for me because of that reason, because it just felt like I'm memorizing a list of kind of animals that fall into this kingdom or something. I don't really understand the, like it was never explained. It just felt like I'm memorizing a list. Chemistry was always easy because there was always a reason for the list. And it's like, I'm just going to memorize the reason. And I can always come up with the list afterwards. Oh, it's so much easier than biology. All right. So looking at this transformation map, remember the B. The two things the B does: reflect across the y-axis, which is changing the x-coordinate, right? Or it horizontally stretches and shrinks. Again, changing the y or changing the x-coordinate. Everybody okay with that? What is the B doing to the x? It's multiplying. The H shifts left and right. What coordinate is the H acting on? The x-coordinate, which controls left and right. Everybody okay with that? If I multiply an x-coordinate by a number that's bigger than 1, that x-coordinate is going to get bigger, right? That's the horizontal stretch. If I multiply the x-coordinate by a number between 0 and 1, it's going to get smaller, right? That's basically the same as division. Like multiplying by a half is the same as dividing by 2. It's going to make the x-coordinates get smaller, right? So you're going to shrink. Does that help? We can make the same argument about A and K with regard to Y. Maybe that helps. Maybe it doesn't. We'll do enough stuff with this that the memorizing hopefully won't be an issue. Okay. So let's do an example here. Okay. So we're asked to describe the transformation in words for this function g of x. So what I'm going to need to use first is this general form for the transformation of any function. And I'm going to use this to identify the values for a, b, h, and k. So a is 2. B is -3. Here's the tricky one. What's h going to be? -1. Well, notice there's a negative sign here. So +1 I really need to think of as minus a -1. The easy way to kind of remember this is that the h is always the opposite sign as it appears in your function. So my general form for the transformation, I have x minus h. How do I turn x plus 1 into x minus something? Well, it's got to be x minus a negative. And then the k is 5. Everybody okay with how I identified those? Now I'm just going to go through my criteria. Since a is positive, I have no reflection across the x. Since the absolute value of a is greater than 1, I have a vertical stretch. by a factor of 2. Since the b value is negative, I have a reflection across the y-axis. Since the magnitude of b is greater than 1, I have a horizontal stretch. 3. Since the h is negative, I'm going left 1 unit. And since the k is positive, we're going up and 5 units. So when we ask for a description like this, we're just going to kind of justify based on the criteria we had before and state what happens. Is that okay with that? Again, the hardest part is making sure you've identified the values for A, B, H, and K correctly. And after that, you're just comparing those to the criteria. Okay. One more example and we'll be finished up here for today. Okay, so if f of x is equal to x squared, g of x, or we're going to graph then g of x equals 2 times f of x, or I'm sorry, f of x plus 3 minus 1. So I'm going to start this same way and identify my values for A, B, H, and K. Who can tell me my value for A? 2. Is everybody okay with that? A little bit trickier, who can tell me my value for B? Yes. Close. It's 1. So notice that I have no coefficient in front of my x, right? What coefficient is there when there's no coefficient written? 1. So I have like really 1 over 1 there. So it's a kind of tricky. At least the first time you see it. After that, it becomes easy, right? Because that trick only works one time till you've seen it, and then you know what to do. The h is -3. That trick of the flopping the sign on the h gets kids all year. And then the k is -1. Everybody okay with that? So using this, what I'm going to do is I'm going to use that transformation map that we wrote down at the very beginning. So in this case, we're going to have 1 times plus -3, 2 times y plus -1. Everybody's okay there? So what I'm going to do now is I'm going to just use some values from y equals x squared, some ordered pairs there, and do this transformation on them. Okay with that plan? So for example, -2, 0, 0, and 2, 4 are all points for y equals x squared. Right? If I plug -2 in for x, I get 4. Right? If I plug 0 in for x, I get 0. If I plug +2 in for x, I get 4. Everybody's okay with that? Now, how I pick those points to plug in, we're not going to worry about right now. I would probably give you the function and label some points on it, but in the interest of time, I'm just going to tell you the points right now. So what I'm going to do then is, these are my pre-image points, and I'm just going to find their image using my transformation math. So I have 1 times negative 2 minus 3, and then 2 times 4 minus 1, which is negative 5, 7. And I do that for each of these. And I have this. So my original function, or my pre-image function, looks like this. And my resulting function here, I'll do that in green, I guess. So negative 5, 7, negative 3, negative 1, and then negative 1, 7. Looks like this. So if you look, it looks like this graph has been shifted to the right, or I'm sorry, to the left a couple units, 3 units, moved down 1 unit, and then kind of stretched vertically, like it's got a little bit taller and skinnier versus the original. Does that everybody see that? Okay. So that's good. Good for today. For your guys' homework check on Sunday, you're going to have homeworks 2 and 3. Next week, you guys will do we'll take a day in class to work on the test review. That's what the asynchronous learners are doing tomorrow is their test review. And then we'll take a day after that. We'll talk about the test review, talk about what the test is going to look like. Probably start chapter 2. And the class period after that, we'll do the chapter 1 test. Okay with that? I'm not sure what day of the week that is, but it's not next week. It'll be the week after, because there's only 2 class days next week for everybody. Because we don't have school on Monday. Because it was Labor Day. Everybody okay? Okay. That's all